Good morning, everyone. We are from Group 9 from 12 Fausti, and today we are going to discuss the various word problems that highlight the concepts of work and kinetic energy, gravitation and elastic potential energy, and mechanical energy.
Problem number 1. A 12-kilogram package in a mail sorting room slides 2 meters down a chute that is inclined at 53 degrees below the horizontal. The coefficient of kinetic friction between the package and the chute surface is zero point 0.4. What is the net work done on the package? Here are the following given values based on problem 1. Mu sub k, or the coefficient of kinetic friction between the package and the chute surface is equal to zero point 0.4. M, for mass of the package, is equal to 12 kilograms. The angle, or theta, is 53 degrees. X, or the distance, is equal to 2 meters. And the gravity present is equal to 9.8 meters per second squared. The general formula on how to get the network would be the work done by friction, gravity, and normal force. For the first, which is friction, the formula would be the given coefficient then multiplied by mass, gravity, distance, and degree of cosine. After that, input the values portrayed in the given, which is zero point 0.4 times 12 kilograms, then 9.8 meters per second, then 2 meters, then 180 degrees of cosine. All in all, the work done by friction would be negative 56.30 joules. After that, the formula for gravity would be mass, then multiplied by gravity, distance, and degree of cosine. Forward to that, input the values given, which are 12 kilograms, then 9.8 meters per second squared, then 2 meters, then 37 degrees of cosine, wherein it is subtracted from 90 degrees to 53 degrees. All in all, the work done by gravity would be 180 joules. On to the last. The formula for normal force would be the normal force highlighted then multiplied by distance and degree of cosine. Further, input the values given, which are 0 newtons multiplied by 2 meters, then 53 degrees of cosine. The normal force is 0 because the basis for that is cosine 90, wherein the line value is observed is 0 as 0. All in all, the work done by normal force would be 0 joules. To reiterate, the formula for network would be the final value for work done by friction, gravity, and normal force. To encapsulation, the final values would be negative 56.30 joules, 180 joules, and 0 joules. To add them all up, the network is 123.7 joules. In conclusion, the work done by the package is 123.7 joules. Problem number 2. A 4.80 kilogram watermelon is dropped from the roof of an 18-meter tall building and feels no appreciable air resistance. Calculate the work done by gravity on the watermelon during its displacement from the roof to the ground. From problem number 2, there are three given values found. The mass of watermelon, which is 4.80 kilograms, the height of the building, which is 18 meters, and the constant gravity, which is 9.80 meters per second squared. Using the work formula, we can determine the amount of effort that gravity did to move the watermelon from the roof to the ground. The formula of work is equals to mass times gravity times height. By substituting the given values to the formula, the equation will be work sub gravity equals to 4.8 kilograms times 9.8 meters per second squared times 18 meters. With multiplying the three given values, we would have the final answer of 846.72 joules. Thus, the work done by gravity on the watermelon during its displacement from the roof to the ground is 846.72 joules.
Problem number 3. A spring of negligible mass has a force constant of K is equals to 800 Newton per meter. How far must the spring be compressed for 1.20 joules of potential energy to be stored in it? With problem 3, the elastic potential energy of 1.20 joules and force constant K equal to 800 Newton per meter are both given in which x or the distance of how far the spring must be compressed is being asked. We'll be utilizing the formula of elastic potential energy, which is equal to force constant K times x squared over 2 or 1 half times force constant K times x squared. We then multiply both sides of the equation by 2 over K to isolate x squared. We then get the square root of x. Thus, having the equation of x equal to the square root of 2 times to the elastic potential energy or 2u sub EL over force constant K. From the new equation, we substitute the given values. This makes the equation x equal to the square root of 2 multiplied with 1.2 joules over 800 Newton per meter. Thus, we'll be able to derive with the final answer of 0.55 meters of or 5.477 times 10 to the power of negative 2 meters in terms of scientific notation.
A 1.50 kilogram snowball is fired from a cliff 12.5 meters high. The snowball's initial velocity is 14 meters per second, directed 41 degrees above the horizontal. Using the conservation of mechanical energy, calculate the speed of the snowball as it reaches the ground below the cliff. The given values of problem 4 are the following. Mass is equals to 1.5 kilograms, height of the cliff is 12.5 meters, the snowball's initial velocity or v sub 1 is equal to 14 meters per second, the angle which is 41 degrees, and the constant value of gravity which is 9.8 meters per second squared. We'll be utilizing the work energy theorem, which states that the total work done is equal to the final kinetic energy minus the initial kinetic energy. Since we are looking for the final speed, we'll be using the final kinetic energy. The equation of final kinetic energy is equal to the total work plus the initial kinetic energy. From that, the equation we'll be using is mass multiplied with final speed v sub 2 squared over 2 equal to mass times gravity times height plus mass times initial speed squared over 2. To isolate the final speed, we divide both sides of the equation with 2 over mass m and transform it to its square root. Thus, the final speed equation is equal to the square root of 2 times gravity and height plus initial speed v sub 1 squared. In substituting, the given values of the equation becomes the final speed, which is equal to the square root of 2 times 9.8 meters per second squared times 12.5 meters plus 40 meters per second squared. We then arrive at the answer of 21 meters per second as the final speed. In conclusion, the speed of the snowball as it reaches the ground below the cliff is 21 meters per second. An 80-kilogram skydiver jumps out of a balloon at an altitude of 1,000 meters and opens the parachute at an altitude of 200 meters. A. Assuming the total retarding force on the diver is constant at 50 newtons with the parachute closed and constant at 3,600 newtons with the parachute open, find the skydiver's speed when he lands on the ground. B. Do you think the skydiver will be injured, and explain? And C. At what height should the parachute be open so that the final speed of the skydiver when he hits the ground is 5 meters per second? With problem 5, letter A, the given are the following. Mass is equals to 80 kilograms. The constant gravity is 9.8 meters per second squared. Initial distance is y sub I is equals to 1,000 meters, and the final distance is y sub f is equals to 0 meters. Since there are two given forces, we'll be labeling the least force, which is 50 newtons, as F sub 1, and the most force, F sub 2, is equals to 3,600 newtons. It is also applicable with a given distance where d sub 1 is equals to 800 meters, in which it is from 1,000 meters minus 200 meters, and 200 meters is d sub 2. Lastly, the initial velocity or speed is equals to 0 meters per second, and letter A is looking for the final velocity. We'll be applying the conservation of energy equation to the given situation, which is the difference of kinetic energy plus the difference of potential energy and plus the force of air multiplying with a distance equals to 0. where the retarding force of air is the same as friction. For our purpose, the difference of kinetic energy is equals to mass times to the final velocity squared over 2 minus mass times the initial velocity squared over 2 plus the difference of potential energy, which is mass times gravity times final distance y sub f minus 2 mass times gravity times initial distance y sub I plus to the product of force and distance, which is f sub 1 times d sub 1 plus f sub 2 minus f sub 2 times d sub 2 equals to 0. Since both initial and velocity and final distance is 0, the equation will be simplified. From there, we would isolate the final velocity and utilize the square root. Thus, the equation of final velocity is equal to the square root of mass times gravity times y sub I minus f sub 1 times d sub 1 minus f sub 2 times d sub 2 over mass. We then substitute the equation with the given values to derive with the answer of final velocity equals 24.5 meters per second. Thus, the skydiver speed when he lands on the ground is 24.5 meters per second. If the total retarding force on the diver is constant at 50 newtons with the parachute closed and constant at 3,600 newtons with the parachute open. For letter B, the answer will be yes, since the speed of the skydiver is velocious for safety causing him to have a possible injury. Moving on with letter C, we'll be using the same values except the final velocity is 5 meters per second and we are looking for d sub 2. First, we must apply the concept of conservation of mechanical energy where the overall difference of kinetic energy plus potential energy and the force of air as related previously. We'll be utilizing now the formula by substituting certain values in the equation. So 1/2 times the mass and initial velocity times mass times gravity and initial distance y sub I plus the initial value for force and distance and final value for force and distance. After that, substitute the initial distance when the parachute opens, which is 1000 meters minus d sub 2 in the initial distance. And then we'll transpose the equation where the final distance can distribute itself on both initial and final velocities, while for the initial velocity, it can distribute to the 1000 meter given value. After that, we'll be isolating d sub 2, so the equation will be d sub 2 equals mass times gravity times y sub I minus mass times final velocity squared over 2 minus to the product of 1000 meters times initial force over the difference of f sub 2 and f sub 1. And then we then substitute the equation using the given values, which results where the final distance of the parachute when the final speed of 5 meters per second will be 206 meters. Thus, when the final speed of the skydiver is 5 meters per second when he hits the ground, the parachute should be open at the height of 206 meters.
And that concludes our video for today. Just remember, where logic will get you from A to B, imagination will take you everywhere by Albert Einstein. Again, we're Group 9 from 12 Fausti and AMDG to all of you.